Chapter 8 will be the inverters topic. So we have discussed so far, we discussed DC to DC converters. We discussed AC to DC rectifiers, right? We discussed AC to AC voltage controllers. I would not say power converters because there are many topologies. I think you guys are going to be exposed to a lot of the AC to AC converter topologies. There are many types that we will not discuss here or here actually, but the last sort of area that we want to discuss, or converters that we would like to discuss, are the DC to AC converters, and these are called inverters. Right? We discussed a little bit about inverter operation in our rectifiers topic, and this was a very special type of inverter. I mean, it's a thyristor-based inverter. I mean, they are used typically at very high powers because thyristors are very rugged devices that you can use at high power. So some very high power drives are driven by inverters that are thyristor based, right? Very high power, like 20 megawatt based drives, etc., etc. We will be talking more about PWM, pulse width modulated DC to AC inverters in this section, in chapter 8. Okay, so the objective is, of course, we would like to create as nice of a sine wave as possible. That's the final objective. We will be skipping. I know this looks like a lot, but we will be skipping a lot of stuff, and a lot of this will be things that we have to know. Just draw the circuit, draw some waveforms. So it's something. It should not be too much of a problem. Where do we use these inverters? Again, anytime we want to convert from DC source to an AC load, like adjustable speed motor drives, uninterruptible power supplies, hybrid vehicles. There are many applications of inverters. One of the simplest inverter topologies is something you are actually building in the project, which is the full bridge inverter, right? So you are building that with the purpose of creating DC at the end, right? But in the intermediate stage, you're creating high frequency AC, right? So you have our full bridge inverter. Looks something like this. You have your DC power supply here. Again, remember our trick that we talked about here. The way I would like to represent this is the same way I discussed the DC to DC converters as well. So I can represent this full bridge converter using this simplified representation that I discussed when we discussed DC to DC converters. Right? I have a pole here, or an arm here that's moving between these 2 points. And I have one here that's also doing the same. I just happen to have the same DC voltage applied to this arm and same DC voltage applied to this arm. The other thing is we always said that here across these switches, which I represented using this sort of arm with 2 contacts, right? Across them, I always have a fixed voltage, right? A stiff voltage. Remember we said in the buck converter, the stiff voltage is the input voltage. In the boost converter, the stiff voltage is the output voltage. In the buck boost converter, that stiff voltage is the V input minus V output, right? Here, I have the same thing. I have a stiff voltage here. That's always equal to this VDC, or the V input voltage. And at the output, I always had in the buck, or the boost, or the buck boost, I had the switch current going through an inductor, right? And it's the same here. I can draw this as half the inductor here, half the inductor here. They're in series anyway, right? And then this is my load for my inverter. This load can be a resistive load, so I can put this load here. It's coming. There's an inductor here, and I drew an inductor here, and then I can draw a resistor here, and maybe I put a capacitor as well. I can, right? Or maybe not. Right? Whether or not I put a capacitor will depend on how much ripple voltage I want to maintain across my load, right? So it's up to us later to decide if we put a capacitor or not. But if I want to select the switches that I put in here, I can go back to slides of the first chapter, right? The first chapter slides. What do I see here? current is in this load, I want to create AC current, right? I want to create current that is going to go into this node or out of the node, right? So it's going to go into this node or out of this node, right? But the voltage doesn't change polarity, right? So if we go back to this chapter 1 slides, that table that we had with how to select switch architecture, right? I have current here, positive, and current here, negative. Voltage is only in one polarity, right? My voltage here does not change polarity, right? My voltage is always in the same polarity. My current is changing, is either positive and negative, right? So I have to consider this architecture or this selection of devices as well as this selection of devices, right? So I have to find a way to combine these two, right? So how can I combine these two? You can go about it step by step. I want to combine the top two switches either in series or parallel. I want to combine the bottom two switches either in series or parallel. That's the only options that I have. If I take this switch and put it in series with this diode, I cannot do that because this switch is pushing current in one way and this diode is pushing current in the other way. If you put them in series, then you will have a switch here and a diode here. This wants to push current this way, this wants to push current this way. It will not work, right? So the only way to combine these would be to put the switch and the diode in parallel. If we do that, then we can allow current to flow this way in a controlled fashion and this way in an uncontrolled fashion, okay? But at least I can have current flow in both ways. And I have to make sure that in this reverse direction, there's another switch that allows me to control current flow in that direction, right? And that, if I do that, then I have controlled current in all directions, right? So that's the objective here. So now I can take this architecture that I came up with here and substitute it with devices if I want to. Before doing that, let's just see what's happening here. So this is V inputs. If I have this top arm connected to this node 1, 2, 3, 4, arm this arm on the left and arm on the right, the arm on the left connected to node 1 and the arm on the right connected to node 4. What's the voltage across my load? What's the voltage across my V output? Exactly. So if I have this arm connected to point 1, this arm connected to point 4, I've taken this load and placed it across Vn. How about if I take this arm connected to point 2, take this arm connected to point 3? What is the output across what is V output equal to? Is it Vn or minus Vn? You flipped it, right? So initially you had this case. This is V output.
You said you had two switches in there that control the current, right? Won't allow it back feed.
No, these are now ideal switches. For now, no. There's this is an ideal switch. This is just an arm that's flipping now. So when I had this arm connected to point 1 and this arm here connected to point 4, this was how my circuit looked like, right? And now if I now make this arm connected to point 2 and this arm connected to point 3, then the circuit would look like this. Current here was flowing this way. How about current here? The opposite way, right? So in one configuration I'm putting V input, in the other configuration I'm putting minus V input, right? If this is the polarity of V output, I flip the polarity of V input across it, right? So I have V input or minus V input. Do you agree? Okay. Another way to look at it How about if I do this? How about if I connect this arm to 1 and this arm to 3? What do I have across my V output? This arm to 1? Yeah, I would have 0. How about if I have this arm connected to 2 and this arm connected to 4? 0. So this converter topology allows me to get an output voltage. V output is equal to V input, or minus V input, or 0. Right? So I can get 3 levels of output. Okay? I can think of this in a different way. That's something more like what we've been discussing in DC-DC converters, right? So if I have this configuration, just this half of it, just looking at half of this thing, okay? This is operating with a duty cycle of D1, right? And this is my V input. We said that the average voltage I see here is always going to equal what? What's the voltage I will see here? It's either V input or no, 0. This is 0, my reference, or and this is V input. So the voltage here is going to be between 0 and V input, 0 and V input, 0 and V. So its average value is going to be between 0 and V input. But what is it equal to? In terms of D1? Exactly, duty cycle times? Exactly, so it's equal to duty cycle times V in. Right, so I have duty cycle times V in coming from this side. Right, I would like to look at V output. If I want to look at V output, I have V output here. V output is I want to know what my V output is equal to. Then I have to look at the voltage here minus the voltage here to see what my V output is, right? So now I looked at the left hand side. My voltage is D1 times V input. Assume now that I don't allow for this 0 state. If I don't allow for this 0 state, then I'm always going to operate with how? I'm always going to have this arm at 1 and this at 4. Or this at 3 and this at 2. I will never have this 1, 3, and 2, 4 configuration, right? So let's now, for now, just forget about this 0 operation. If I do that, that means I'm operating this other side of the other side of the converter. So let me draw the other side of the converter here. Here I can draw the same V input across it, right? And here. I don't want to know what my voltage here looks like. This is same V input, right? So what is the average voltage here? What does that look like? Exactly. 1 minus D1, which is the same duty cycle, because I said that if this is the top, this is the bottom. This is the bottom, this is the top. So they're opposites of each other. So for the switching period, if this is D1, this is 1 minus D1. It's 1 minus D1 times same V input, because they're the same. They're the same, right? They're connected to the same DC input, right? So on one side I have D1 times V input. The other side I have 1 minus D1 times V input. So what is V output? V output is the difference between the two. So V output is equal to D1 times V input minus 1 minus D1 times V input. So it's equal to what? D1 V input minus 1 V input plus, right? D1, right? So it's okay. So 2D1 V input minus V input, right? Or V output is equal to what? V input 2D1 minus 1. So if duty ratio is equal to 0, what's my V output? Minus V in, exactly. If duty ratio is equal to 1, What is my V output? V in. Right? So my V output will range between minus V in to V in, depending on the duty ratio, which confirms what we were talking about here with this flipping business. Right? So you know you can now derive it easily, and we can do this for the half. So this is called the full bridge converter. The voltage, the range of operation, range of output voltage for the full bridge inverter is minus V input to V input, right? That's because I chose these to be complementary, right? If I am to include this zero operation, right? How will I write this? How will I write this? Can I write this as 1 minus D1? No, I will have to write this as D2, D2 times V input. And then the output voltage will be, you know, D1 times V input on this side, minus D2 times V input on this side. So the output voltage will be V input D1 minus D2, right? And in this case, if D2 is 1 minus D1, then I will operate only between minus, I can only operate between minus V input and V input, right? If I want to get zeros, I can make it 0. I can make these two duty ratios the same, right? If I make this 0.5 and this 0.5, then I can get a 0 as well, right? If D2 is 1 minus D1, I will operate between these 2 points. If I want to get the zeros to function, then I can operate in this fashion. What is the benefit of the zeros or not? We will talk about that next time. But I just want you to get a feeling of the operating range, and then we can do the same thing for the half bridge inverter. There's something called the half bridge inverter topology, and the half bridge looks like this. These are two capacitors, and this is my same representation. So this is operating with D1. What is the voltage here? Average value? V in times D1. What is my voltage here? This is the capacitive voltage divider. So this is V input here. This is V input over 2. Two capacitors across the DC supply. It's a capacitive voltage divider. This will be charged to half. This will be charged to half. So my output voltage now is equal to what? V in times D1 minus times V in over 2, right? This is my output voltage. I'll take output voltage between these two nodes. We saw that with this topology, I can have a load here. Let's assume it's a resistive load in this case. For a resistive load, if I turn on switch 1 and 2, I'm placing VDC across, this is my V output polarity. So my V output polarity is always fixed. So if I'm turning on 1 and 2, V output is equal to VDC. Right? If I'm turning on 3 and 4, V output is equal to minus VDC. I flipped it, right? So this is one way to operate these converters, right? So you just turn 1 and 2 on, and then turn 3 and 4 on. 1 and 2 on, turn 3 and 4 on. And that's what you're building. You're building that after the 12-volt battery charger, right? You're building a high-frequency AC converter. That's what you're doing, right? This is AC, this is not DC, right? Why are you doing that? You're doing that because you want to boost the voltage. You want to use a transformer because you want to boost the voltage from 12 volts to 180 volts. And you cannot use a regular boost converter because we saw the limit on boosting ratio is what? 4 times, for example. So from 12, you cannot boost to 180 volts. No way. So what's the solution? The solution is always a transformer. AC, but transformers do not allow you to translate DC voltages. They only allow you to translate AC voltages, right? The other solution is you can use 2 boost converters in series, right? If you boost 2 boost converters in series, so 12, you can multiply this by, let's say, 4. What do you get? 48. Multiplied by 4. No, it's closer to 200, right? It's 200, 200 minus 8, right? It's 198, right? 192 volts, right? So you can get your 180 volts. Sure, great. But then you have an efficiency here and an efficiency hit here. What's the total efficiency now for your DC stage, for your boosting stage? If this is, let's say, 90%, and this is 90%, your efficiency would be 0.9 times 0.9, 0.81. So 81% efficiency for the boosting stage. So this is one way to do it, right? Another way to do it is what you're doing in the project. What you're doing in the project, you have a full bridge inverter that you are creating a high frequency AC waveform from. This high frequency AC waveform, is it a nice, beautiful sine wave? No. And I don't care for it to be, because I'm going to rectify it afterwards, right? In your case, in the full bridge DC to DC converter, when you make a full bridge DC to DC converter that has a front end, basically, which is a high frequency DC to AC inverter, you don't care about the frequency content. But if you do the Fourier series for this, what will you find? You will find a lot of harmonic content, because it's a square wave. A square wave will have, again, if you go back to our Fourier series, here, this is the Fourier series for the square wave. V of t is equal to 4 V maximum over pi. All of these harmonics, first, third, fifth, seventh, it will contain all of these harmonics. Do I care? In your case, in the case of building a DC to DC converter, which you're going to take this waveform and rectify after that, you don't really care. You're not taking this into a load and looking at the power factor or the power transfer or whatever, because you're going to convert this to DC. When you convert this to DC, it's going to look like a nice DC waveform at the end, right? So you're going to rectify this. It's going to look like a DC waveform at the end, but you get the benefit of being able to go through a transformer by doing this, because you have an AC waveform. You can push that to a transformer. If you put DC across a transformer, the winding will not generate back EMF to oppose the voltage that's being placed on it. If there's no voltage to oppose the back EMF, if there's no back EMF voltage generated to oppose the voltage that you're placing across the winding, you place a voltage across a winding here. If this winding is not going to generate an opposing back EMF, meaning will look like this, having a voltage source in series, that's the equivalent circuit of a back EMF voltage developed across the winding. If the winding is not going to do this, then what's going to happen? Then you're placing a voltage source across a piece of wire, basically. So the resistance of the wire will limit the current. That's it. So you're going to be pushing a huge amount of current through. Pushing a huge amount of current through, you saturate the transformer. It's useless. You're not building a transformer anymore. You're building a heater, right? So only when the winding is able to generate the back EMF, and when is it able to do that? When you push an AC waveform through it. E equals, the back EMF is equal to N d phi by dt. The back EMF voltage developed across any coil is equal to number of turns multiplied by d phi by dt, the time varying value of flux, right? So it has to be an AC component, time varying component, to be able to push it through a transformer, right? So you do this in your circuit, right? After that, you push it through a transformer and rectify it. The classical rectifier that we studied, the diode rectifier, the full bridge diode rectifier that we studied at the beginning, right? No problem. This is great. And the equivalent circuit to what you guys are doing is the same as what I've been talking about, right? This is, at the end of the day, your transformer, right? It has, what's the model of a transformer? What does the model of a transformer look like? It has a leakage inductance and the leakage and the resistance of the winding, then ideal turns ratio, and then the leakages on the secondary side. And then if you want to consider the magnetizing branch, you can consider that as well, right? From 338, this is the equivalent circuit of the transformer. So there is an inductance in series as well. So same thing, I have my two switches, have a voltage across them that is fixed. And my output is going through an inductor, right? Nothing changes. All the power electronics topologies are the same. Always the two switches that are operating complementary have a fixed voltage across them. And between them, then there is an inductive current at some sort. You don't. It can be a transformer. It can be a big inductor. It can be a small inductor. It depends on your circuit's operation, right? So anyway, so you have these this inverter now that is creating this V output that is either minus V input or V input, right? If you are operating it in a complementary 1, 2, 3, 4, 1, 2 together, 3 and 4 together, right? And we operate with a duty cycle, a fixed duty cycle, right? If you go ahead and have a fixed duty cycle, but here we're operating. What's the switching frequency that we're operating at? What's the relationship between the output voltage frequency and the switching frequency? This is the frequency of the output. Okay. This is my output waveform, right? It's either Vin or minus Vin. When 1 and 2 are on, it's Vin. When 3 and 4 are on, it's minus Vn, right? So this is my period. So what's my switching frequency for operating an inverter in this fashion? What's my switching frequency? It's equal to the fundamental. It's equal to the output frequency, right? This is my output waveform. I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here. Then I'm operating switch 1 and 2 here. Right? So what's the switching frequency of switch 1 and 2? It's the same as the output frequency, right? It's happening one time every switching period. One time every switching period, right? So it's the same as the output frequency. You agree or not? Guys, come on. Huh? Why not half? No. No, I mean, remember this is a waveform. It's happening. I have a pulse here. Pulse here. What is the frequency of this waveform? You look at the period. And this is the period. So Fs is equal to 1 over the period. Right? It doesn't matter if this is this wide or is this wide. Right? Does it matter? It's turning on and off during a period. That's the switching period. It's turning on and off one time during this switching period. So what is the switching frequency? It's 1 over the switching period. Right or wrong? No, this is a question that I need an answer for. Yeah. Yes? You're not convinced? Yeah.
I don't get how it's the whole period. Like switching what is the switching frequency in this diagram?
Switching frequency is 1 over the switching period. So think of, okay, you take 4 classes. Does it matter? You take 4 classes a day. That's your frequency of classes. Does it matter how long the class is? Right? So this is happening. You're turning on the device and turning it off once every period. Once every period. This is my switching period. Right? The turn on duration. You're confusing duty cycle now with the period. Right? Your duty cycle is the time on over the time on plus time off. Or this is now the full period. You're confusing both now together. So I'm not asking for the duty ratio, I'm asking for a period, right? Or the inverse of that is the switching frequency. So how fast am I switching devices 1 and 2? I'm switching them one time during this period. So their switching frequency is 1 over this period, right? So this is the frequency of the output. So if I'm supplying a 50 hertz or a 60 hertz system with this inverter, I can, right? Would it be a problem if I plug this computer into this outlet that is being supplied by an inverter that's feeding a waveform like this? Maybe. It depends on the input specs of this. If the input of this PC is nothing but a full bridge rectifier, no, it doesn't matter. the input is a full bridge rectifier, if it's taking this AC voltage and just rectifying it, it does not really matter at all. It does not really matter at all. If it's a different thing, if it's something, if it's a circuit that's intelligent enough to detect, okay, I have too much harmonic content, so I'm gonna be just heating up my board without transferring real amount of power to the system, right? Lots of current, lots of voltage harmonics, for example, or if this is a current waveform, lots of current harmonics with no power transfer. Then it's a different problem. Some equipment will tell you, we allow for distortion, voltage distortion of a certain amount. You exceed the voltage distortion, I will shut down. It's like the thermal shutdown we talked about the other day, right? So, but yeah, you can plug this, you can take this inverter and supply an AC load, and no problem, it will work. And the benefit here is I'm switching at a very low frequency, so my switching losses are very low, right? My switching losses, turn on and turn off switching losses are very low, and I'm supplying an AC waveform. It's nice, it's great, but I have a lot of harmonic content, right? The alternative to this is to figure out a way to improve the harmonic. I mean, if you want to create a nice sine wave, you have to figure out a way to create the sine wave, and it's not going to be by switching at fundamental frequency anymore. You have to switch faster to be able to chop up this waveform in a way that it would make it resemble as a waveform that has less content, less harmonic content. So initially, so now we started with this simple 4-switch inverter, and we're operating the switches at fundamental frequency. And we're getting, and this is my 50 hertz, this is my 20 milliseconds. If this is a 50 hertz waveform, this is V input, and this is minus V input. Am I going to be able to run my load? Yes, I can. If I connect a heater, is it going to bother the heater? No. The heater will not be bothered at all. If this is my voltage waveform, I have a resistor. I have the current waveform will look exactly the same, and which means I have what? I have voltage harmonics and a corresponding current harmonic. Voltage harmonic corresponding. That means I will be able to transfer full power. I will not be losing power. Remember when we were talking about harmonic losses, it was because I have a sinusoidal voltage and distorted current. In that case, I have pure sinusoidal voltage at the fundamental frequency, and then currents at the fundamental, and many others. That many other stuff will not count, because the power is equal to V times I at a certain frequency times the cosine angle between them. If I don't have V's at the rest of the I's frequencies, then it's useless. Then all of these other currents are not helping me deliver real power to the system. But here, it's a square wave voltage. If I have a resistor, square wave current, no problem, life is great, right? But if I have an RL load, the current will not look exactly like the voltage. So I will have there will be some content in the current waveform that is not in the voltage waveform. So I will have some losses there. But assuming it's a resistive load, then this is perfectly fine. The problem is it has a lot of harmonic content. This is something that exists. And if I have an RL load, having a lot of harmonic content means that I have losses. I have current harmonic components that are not contributing to real power transfer, right? So for a resistive load, no problem. It doesn't matter. This is fine. Put a heater, yeah, it will operate as good as anything else. Put an RL load, any other real type load, then you will have a current waveform that will. How will the current waveform look here? RL load. How will an RL load look in this case? I'm putting this voltage across an RL load. What will the current look like? Again, assume it's an inductive load, okay? Assume it's an inductive load. If it's an inductive load, what will the current look like? A ramp. Where is the maximum value for the ramp? Here. Where is the minimum value for the ramp? Here, or also here, because I'm periodic, right? So it's a ramp if it's a pure inductive load. How about if it's not a pure inductive load? It's an exponential. So the exponential, it will look like this. It will look like this, right? The harmonic content in this blue waveform is not equal to they're not equal. I mean, this is a square wave. This is the Fourier series for the square wave. We just saw it, right? We just saw that it's V maximum over pi and then all the triplet harmonics. First, third, fifth, so not triplet, first, third, fifth, seventh, etc. So that's the Fourier series for the square wave. Is that the same as the Fourier series for this waveform? No. They will have some harmonics that are in phase. So they will have maybe the fundamental. They may have a third. They may have a fifth. But definitely, this square wave has transitions, significant transitions here. That means that there's a lot more harmonic content in these transitions, fast transitions, than this slow transition. There's a difference. I don't have the Fourier series for this blue waveform. But since the waveforms are not identical, then there's a difference between the harmonic content. That's the basics of the just by looking at the waveform. If that's the case, that means I have some voltage harmonics that will not find a corresponding current harmonic at the same frequency, and hence will not be able to transfer real power. Is that good or bad? Bad, because I want to deliver AC power to my load. But I have current flowing that is not contributing to P equals V times I cosine phi, which is, these have to be Vx, Ix, same frequencies. If there are currents that are not at the same frequency, then it's useless. I'm not contributing to real power, right? So what do we want to do? We would like to be able to improve the load will not change. So the current is sort of dictated upon us, right? The current is going to be dictated by the load, right? You put a voltage, you create. So ideally, I would like to go and be able to create a nice, beautiful sine wave. That's ideal, right? But before doing that, people developed this in stages, right? So first we had this 4-switch inverter operating at the fundamental frequency of the output. Then, what's another capability I can do with, so this I'm operating either 1, 2, I'm operating either 1, 2, or 3 and 4 together, right? Either 1, 2, or 3, 4. 1, 2, or 3, 4. So it's either Vin or minus Vn, Vn or minus Vn. What's some other option we talked about last time for operating this inverter? I can get Vin minus Vn, and what else can I get out of this inverter at the output here? 0. If I turn on 1 and 4, or I turn on 2 and 3, I can get 0. So let me show you this. So would this be closer to a sine wave or not in harmonic content? This is a square wave with a ton of harmonic content, right? This is another waveform. I've added a 0 here. What does a sine wave look like? A sine wave looks like this, right? Sine wave looks like this, right? There's a huge difference between these two here, right? A huge difference between these two here, right? The closer the two waveforms are together, that's from a physical perspective. You agree that if the waveforms look close to each other, that means probably their harmonic content is similar, right? So now I have something that looks very different at many places here. So I'm trying to get closer to that. So here I add some zeros here and some zeros here, zeros here and zeros here. I'm a bit closer. So you would expect that the harmonic content in this waveform would be less than the harmonic content in the square wave, right? So people went on a little bit further. We will look at the equations for all this, but so they started with this, then added zeros. Then, okay, they realized that this is a nice trick to play with. If I add some zeros here and control my pulse width. If I control my pulse width, they realize, okay, it's interesting. I can get better harmonic content. Fine, I have to raise this value of voltage, right? Because if I want to meet the same RMS value, I will have to, of course, raise this. But they found a nice trick. So people said, okay, how about I do this? Maybe I do, instead of 1 pulse, I do 3 pulses. I do a small one here, a bigger one, and a small one here. And maybe I do this, and I do this, and I do this. Does this look closer to a sine wave or not? Here, instead of rising suddenly, like this is a 0 and then a sudden rise in the value here. Here I have, okay, it's like a sudden bump in the average value of the waveform, and then another bump, but with a bigger duration, right? So it seems it's closer to a sine wave, which rises in value, it rises slowly to a higher value. So here it has a small, this area would have a small average value, this area would have a higher average value, small average value, then 0, right? So you're closer to a sine wave, right? So people used to program this. They call this programmed pulse width modulation. And then they developed better techniques to become, so they found this trick of adding pulses helps. So they realized, okay, how about if I add many, many pulses? So how do I, okay, so last time we were talking about, inverters, and we said that, so this same topology, we can produce VDC on the load, minus VDC on the load, or 0, right? Depending on which switches we operate. And we drew the single pole double throw equivalent of this, meaning when I say single pole double throw, I'm referring to this configuration, right? This generalization of the two switches that represented as, two nodes here with an arm oscillating between them. So we drew the equivalent circuit of that, and we derived the average voltage between the reference and this node for on one side, and then the other side is the same. It's the same way to derive it, but if you may be operating with the complementary duty ratio, so if one arm may be operating with a duty ratio of D1, and the other arm may be operating with a ratio of 1 minus D1, or one arm may be operating with D1, the other arm may be operating with D2, right? Because the 0 states, to get the 0 states, meaning this is on top and this is on top, then they're not complementary anymore, right? So it's not D1 here and then 1 minus D1. It would be D1 and D2 in that case, right? And we derived both cases, and if D2 is equal to 1 minus D1, we saw the range of voltage being for the full bridge was minus VDC, where VDC was the voltage here, and VDC and minus VDC. That was the range for the full bridge inverter. How about for the half bridge inverter? The half bridge inverter, remember we had two capacitors here, and we had our single pole double throw representation of the switch here, and this was plus minus VDC, meaning the average value here, if this is operating at a duty ratio of D1, this would be average value equal to what? What's the average value of voltage at this node? VDC times D1, and then the average value of voltage at this node, this is a capacitive voltage divider, so it's taking the VDC and dividing it into VDC over 2 and VDC over 2, hence the average value of voltage here with respect to this reference, same reference, is VDC over 2, right? And then so the output voltage for the half bridge inverter was VDC times D minus VDC over 2. This was the average output voltage in this case. So if you take VDC by itself, it's 1 minus, so it's D minus half, right? And so D varies between 0 and 1, so if it's 0, it's minus VDC over 2, right? And if it's 1, it's VDC over 2, right? So the half bridge inverter can provide maximum voltages on the load of plus minus VDC over 2. The full bridge can provide a maximum range of voltage on the load plus minus VDC, right? So it depends on what the output voltage looks like and how you want to optimize the system, because again, you can produce the same output for the same output voltage that you want to produce on the load. You would for the half bridge configuration, you save on switches, right? You only have 2 switches in the half bridge, and 2 capacitors. Versus in the full bridge, you have 4 different switches, right? So you save on the switches. But what happens is, for the half bridge, you would have to bump up the VDC to twice its value for the full bridge if you want to get the same output voltage on the load. Right? To receive the same output voltage on the load, the half bridge converter would need a VDC of twice the full bridge inverter. Right? And we saw that, if you increase the DC voltage that the switches have to block, how does that affect losses? Remember our switching loss? Remember these triangles that we drew? What was the peak value of the triangle? The turn-on losses, turn-off losses. What was the peak value here for the power loss? Exactly. Which V is the voltage that the switch is blocking, and which I, the I that the switch is conducting, right? So if we're blocking double the voltage, then it's going to affect switching losses, right? So it's an optimization process, right? So do you want to live with 4 switches for a full bridge inverter and use less voltage? Or do you want to live with a half bridge inverter and use 2 switches, but then increase the voltage at the input, which means you increase the switching losses. If you increase the switching losses, you may need a heatsink, right? So the cost that you save on 2 switches, you may have to invest in a heatsink, right? And if you want to make it small, definitely go for something without a heatsink. So maybe in that case, definitely go towards a full bridge, right? It depends on how you optimize what the loads requirements are and how the system is optimized, what the ambient temperature is, etc., to be able to choose. Yeah. But I mean, these are 2 topologies that we can utilize to produce AC voltage here. And we said that with both topologies, actually with the square wave, and with both topologies, you can produce an output waveform that looks like this square wave, right? And with the square wave, we went ahead and said that, if this is my voltage waveform, if this is applied across an RL load, what would my current waveform look like? Again, this is a fixed value. That's a DC voltage. If it's a pure inductance, the current will look like a ramp. It's not a pure inductance. There's a RL. There's a resistance as well. So it's an exponential waveform. The solution is natural response plus forced response, and it's an exponential. So the peak value of the ramp would have been here at the end of the positive voltage applied across the RL load. So the same thing will happen for the exponential current. Exponential current will look like this, will look like this, will look like this, etc., etc. Do these have the same harmonic content? No, they look quite different from each other. So then we said that we want to start working on how do we optimize the harmonic content, because at the end of the day, if the voltage and current waveforms have similar harmonic content, right, then you can transfer real power, right? If they don't have similar harmonic content, then you have currents and voltages at different frequencies that do not contribute to real power transfer, right? So that's the final objective here. So this is nice and simple. A nice and simple waveform. You are switching at your fundamental period. So if this is a 1/50 hertz, which is 20 milliseconds, this is your switching period. You are switching. This is your switching period T. Here you have device 1 and 1 and 3 on, and then here you have device 2 and 4 on, for example, right? For the full bridge, the 2 switches across each 1 and 3, and then 2 and 4, 1 and 3, and 2 and 4. You're making the switching every period, once every period. So the switching frequency is 50 hertz. So switching losses, we said, are proportional to switching frequency, right? It's the voltage times the base, the half the base times the height of that triangle multiplied by the switching frequency. So here the switching frequency is so low, which is great. So you have very low switching losses, right? So this is a nice approach. The idea of switching at fundamental frequency once every fundamental period is a nice thing. So there's a family of converters that was developed to make use of that. And then there was a family of converters developed to try to not make use of that and try to switch multiple times to increase the switching frequency, right? So there are two main families of converters we will discuss, of inverters, that we will discuss. So again, just back to the current waveform. So we said that the current waveform for this voltage applied across an RL load would be the natural response and the forced response, right? The forced response would be basically the DC voltage divided by the resistance, right? And the natural response is the same as what we've been doing before, AE to the minus T over tau. Where would you get A from the initial conditions? What are the initial conditions for current? We just had the waveform for current up here. But my initial condition for current was, this is my voltage waveform again. And this is my current. Again, it's a periodic current, so these are equal. And this would be I minimum, some I minimum. And this is some I maximum, and the current will always go to the same value of I maximum, right? So let's see what. So I know that at t equals 0, current is at I equal to I minimum, yeah. Right? So the current waveform is equal to forced response plus natural response. Now forced response is the DC voltage or the source that you have divided by the resistance. Here you have a DC source and you have a resistance and inductance. In steady state, inductance is a short circuit and your source is DC, so it's VDC over R. That's your forced response. Natural response is AE to the minus T over tau. That's between 0 and T over 2, right? Between 0 and T over 2. You have one type of natural response for the circuit. And then at T of 0, we said the current will equal its minimum value. So at I of 0 is equal to I minimum. And then from here you can calculate the value for A and substitute it here. And then from T over 2 to capital period T, you have minus VDC over R as your forced response, right? And then BE to the minus T over tau, with the shift of axis, equal to T over 2. And how would you find B? Same issue. B is equal to at T equals 0, or T equals T over 2 in this case, which is if you substitute with T equals T over 2 here, let me see, I want to zoom in. Right, if I substitute with T equals T over 2, that's my 0 condition, right? In that case, the current is equal to its maximum value at T over 2, right? The current is equal to its maximum value at T over 2, so you will do that. You will, at T equals T over 2, current is equal to I max, and you were able to find B as well, right? So you can find an equation for the current waveforms when it's rising and when it's falling, right? You don't have a single equation for the current waveform anymore, okay? So, from an analysis perspective, what do you think we're going to head after that? If our objective is to look at harmonic content, we're probably not going to use a current equation that's very difficult to come up with a Fourier series for. We would probably go and use you can do that. You have the current waveform. You can try to find the Fourier series for this current waveform. Or, easier, is the voltage waveform. If you have the voltage waveform and you have your impedance, RL as an impedance, you can use your voltage harmonics divided by your impedance at each harmonic and find the current at each harmonic, right? Which is what we did something similar to before. So this is the equation for current from 0 to T over 2 and from T over 2 to T. That's fine. RMS value of current, they wrote that here. Again, they took one of these. They took because the areas are identical. The area on top the area here is identical to the area here. So they were able to, they just did it on half the cycle. So they took the current. So to find the RMS value of any waveform, you would take that waveform, right? Square it, find its average value, and put it under the root. So they took this equation for current here from 0 to t over 2, assuming it's identical, and it is identical because we're applying a square wave. A 50% duty cycle square wave is what we're applying, right? We're just 50%. So the whatever's on top is whatever's equal to the bottom. So that's why they used half only the waveform and multiplied the average value here by 2. Okay? So you can find the RMS value this way. And then one thing I would like to note again is over here when we have VDC on the output, we have certain switches on, right? So if we go back to our circuit, our circuit looked like this. When this switch and this switch are on, I have this output voltage equal to, and this node is connected here, this node is connected here, right? So then the output voltage is equal to VDC, right? So when switch 1, I think they call this 3, are connected, the output voltage is VDC. And when switch 2 and 4 are connected, I think that's what they call them, we will have output of minus VDC because we flip the terminals of the load. We just flip the load across the input. Yeah. So here we have 1 and 2 connected. Here we have 1 and 3 connected, and then here we have 2 and 4 connected. Fine. One thing to note is, let's see what the current waveform looks like. The output current waveform looks like this, right? We agreed that this is what the output current waveform will look like. Is this output current waveform unidirectional? No. Right? I mean, I had it on there. I shouldn't have. I should have waited. I should have asked before. But one thing to note is the current waveform at the output is not unidirectional, right? It ends here with a positive value and starts with a negative value. Did we study a switch that can conduct current in a bidirectional fashion, control current in a bidirectional fashion? No. Oh, switch meaning diode or MOSFET or BJT, right? None of these. All of these switches are able to control current only in one direction, right? So since this is the case, we know that not a single switch solution will satisfy the needs of what I want to do here. And we know that from also that, from the chapter 1 slides, remember that table that we used to go back to. Here we had, I think we had the same polarity for voltage, and then polarity for current was flipped. So we were using, since I have my representation for the single pole double throw configuration here, and I have current here that is bidirectional, right? This is my current. Current is bidirectional. And the voltage is unidirectional. This is my inverter, right? This is my full bridge or half bridge inverter representation. On the output on the load, the voltage is positive and negative, and it's an RL load, right? What does that mean? That means the current will also be positive and negative, right? It's a passive load. You give it a positive voltage to give you a positive current. You give it a negative voltage to give you a negative current. There may be a time delay, right? Depending on if it's an inductive load or a capacitive load, but it's a passive load, right? So since it's a passive load, it will respond in a similar fashion to what you provide. You give positive voltage, it will give positive current. But here I'm giving positive and negative voltage, so I'm expecting that the current will have positive and negative values, right? So current here in the inductor that we have an equivalent representation of the inverter is bidirectional, and this is unidirectional. So I cannot live in one of these quadrants by itself. I have to live in this quadrant, these two quadrants together, right? Current is bidirectional, and voltage has a single polarity. So if you go back to the chapter 1 slides, you have to combine whatever was here and whatever was here together, right? So the combination, the resultant combination that will work is something that looks like this. Current can flow either this way or this way in this device, right? So you have to, I mean, in an inverter application, because, I mean, this is the same switch, right? Here I have switch, as long as I have positive VDC, that means I have this switch and this switch on, S1 and S2 on, right? These are the only switches that are going to be on when when the voltage is positive. But current, even though S1 and S2 are on, current is bidirectional, right? So since current is bidirectional and only these two switches are on, that means that these two switches should allow current to flow in two directions. So I cannot put a MOSFET by itself, or I cannot put a BJT by itself. I cannot do that, right? Because in that case, I will only have current flowing in one direction, right? But this is not true. This is, if you put the ideal switch representation, okay, remove the real switches and just put the ideal switch representation like we have here. When you put the ideal switch representation, you see the resultant current being both positive and negative. So since that is the case, current is both positive and negative, you have to select a device combination that accepts current to flow in both directions to substitute in the circuit in this instead of the ideal switch that we have, right? That is the. Or you could just go to the table, the 4 quadrants that we have in chapter 1 slides, and pick 2 of the quadrants and see how you can combine the switches in series or parallel. And we saw that we discussed this before. We saw with the parallel combination of the MOSFET or the BJT and the diode is what makes sense in this case. Yeah. So that's something to note. And these diodes that are well, no, actually one thing I did not talk about here, I think. Can I have 2 of these switches on at the same time? Can I have S1 and S4 on at the same time? So I cannot have S1 and S4 because I will have a short circuit across the power supply, right? So, and the way I typically operate this is I operate S1 and S2, right? And then maybe S1 and S3 if I want to create some zero output. And then I turn on S4 and S3, right? So S1 and S4 are always complementary. And S3 and S2 are always complementary. But if I, complementary is a nice thing when you talk about digital circuits, right? But everything has a time to respond, right? By the time for you to turn off S1 and turn on S4, there's a time involved. So how close do you do that? Do you turn S4 before you turn off S1 so that you ensure that there's no gap at all? But in that case, there may be a time where you are having S1 and S4 on at the same time, right? Because again, you have S1 on. You want to turn it off and then turn S4 on, right? How fast do you turn S4 on? Do you turn S4 on and then turn off S1? Or do you turn off S1, give it some time, and then turn on S4? Yeah, you turn off S1, and then there's something called dead time that you insert. And here's what it's called: dead time or blanking time, right? This dead time or blanking time is time between the transition of S4 off and S1 off and S4 to be on, so that you don't cause a short circuit or a shoot-through fault is what it's called. Okay, so you always insert some dead time between them. Okay, so and if you look at our representation for the combination of 2 switches as a single pole double throw, this arm that oscillates between these 2 points, it's a good way to think of that, right? It takes time for this arm to move from one point to the other. This time is dead time, right? Why do you need it? Because you don't want to cause a short circuit across your supply. If you make it too big, then remember you're going to be losing parts of your duty cycle, right? You're losing parts of your switching period, right? So if you're losing parts of your switching period, then your ability to control duty cycle is limited, right? So it means that your limit on switching frequency has another consideration as well, this dead time effect that you want to include, right? So it's not the rise times and fall times of the switches only now, it's also the amount of dead time you need to insert, right? Okay, so we talked about the currents being bidirectional. So again, this is the output current, and then if I want to see what switch currents look like, this is switch current IS1 and IS2, and then this is switch current IS3 and IS4, right? Because here S1 is
For that time, that means I'll have 0 in my voltage, and to be maximum then a 0 and then minimum.
for the dead time. Let's see. No, you will have both switches off.
Yeah,
So this switch will be off, and this switch will be off, right? So S1. So sorry, let's draw it. So let's do it for the half bridge, for example. Actually, let's look at it this way. Yeah, when the device when the switch is up here, current is flowing in this direction. When the switch is down here, it's flowing in this direction, right? This is plus minus. This is plus minus VDC, right? So when you in the dead time, actually none of these switches are connected. None of these two switches are connected, but you will have current. Let me draw them actually with the diodes and switches is better, because then you can see that the current will have to flow through the diodes. When the switches are both off, the current will have to flow somewhere. So where is it going to flow? Let's draw the switches and diodes together. It would be easier to see. I think they call this 1 and then this 2. Sorry, my numbering was a bit off. Right? 1, 2, then top one is 3. Top one is 3, and then this is 4. And this is V output. When 1 and 2 are on, current is flowing, and then this is your DC source, VDC, right? When 1 and 2 are on, current flows from the DC source through the switch, through the load, back through the switch, to your source, right? Now we have to insert some dead time. Now I want to switch to what? 3 and 4, right? But I said I cannot switch to 3 and 4 right away. I have to turn off 1, right? And then turn on 4. And then same thing, I cannot turn on 3 right away. I have to turn off 2. And then turn on 3, right? Because that time applies in both cases. So let's see what happens. This is the current, this is the situation now, right? The blue is the situation now. And then we will put the black. So I now turn off 1 and 2, right? And I still didn't turn on 3 and 4. So what's going to happen during that time? Remember, this is an inductive load, right? This is a RL load. So current cannot be interrupted, right? Current cannot be interrupted instantaneously. So since that is the case, so what's going to happen? When I turn off 1 and 2 now, what's going to happen? Hmm? So will current through the inductor change abruptly? No. So this is the same, right? 2 is off, right? 2 is off. I turned off 1 and 2. So where is current going to flow? It cannot go through 2 because it's off. Cannot go through this diode. Cannot go through 3. So it's going to go through this diode. And then it's also going to come through. Did I turn off on 4? I did not turn on 4, so it's going to come through right? And it makes sense. Current has flipped polarity in the supply. My supply current has flipped polarity. Right? So this is the freewheeling time. This is the time where you have, during the dead time, current is freewheeling through these diodes, through the freewheeling diodes. Right? So you will find that, yeah. So this is, let's say this is S1, and then this is D1. S3, D3. S4, D4, S2, D2. So current was flowing in S1 and S2, right? But initially it was flowing S1 and S2. Then what happened? Then it started flowing through, yeah, it started flowing through D4 and D3. And then I turn on what? Then what's, yeah, then I will turn on S3 and S4, right? So if I turn on S3 and S4, what happens? If I turn on S3 and S4, remember this now the inductor current here is now being opposed by the DC supply. Initially it was supplied by the DC supply, right? Now there's voltage opposing current. So what was happening to the current, the blue current? It was decreasing in value. I mean, you have an inductor and you have a voltage source opposing it, so the current is opposing it, so decreasing in value. And now the green, I mean, after you've exhausted that energy in the inductor, basically now you flip the polarity of current by turning on S3 and S4. Yes?
Are we, for that short time, are we charging the source
Yeah, you're returning power is going back to the source.
from the inductor?
Yeah? Right? The current is changing polarity and voltage doesn't flip its polarity. Okay? And then, sorry, so S3 and S4, sorry. And then let's just finish the switches and then we'll do. And then what happens? Then I want to turn back turn off S4 and S3, but I cannot turn them off and turn S1 and S2 right away. So I turn off S4 and S3. What happens to the current? Yeah, so current will not change polarity. Current will continue this way. It will go through D1, right, and D2. Yes, ma'am. What do you mean the waveforms don't change? When S1 and S2 are on, no. And when S1 and S2 are on, what is the output voltage? S1 and S2? Huh? VDC. When S3 and S4 are on, minus VDC, yeah. So it's VDC minus VDC. VDC minus VDC. But when S1 and S2 are on here, during this time, I had a period of positive current, and then I also had a period of, so this is, so I had a period of positive current here. This is S1 and S2, S1 and S2 here. What was direction of current flow here? S1 and S2 current flows this way, right? D, and then so So which one? So the black was positive, and the blue was positive, right? But we said when S1 and S2 here in this period, remember current looked like this? Current looked like this, right? So this was period of positive current. Before it, there was a period of negative current. So and this is repeating. So it seems like this will repeat, right? So this is just a cycle you go through. So this was positive current through the inductor. This is also what? D4 and D3 is also positive current. How about this? Negative, and then this is negative as well, right? So we had a period of negative current and followed by a period of positive, right? What am I doing? Yeah, then here, then this is positive as well, right? So it's negative and then positive, positive, negative, negative, right? So I have negative, positive, positive, negative, negative, positive, positive, negative, negative. So negative, negative, positive, positive. When we go around, I mean, this keeps repeating it, right? So this one here is this S1 and S2 being on, and then I turned off S1 and S2, but I still had positive current flowing, which is this section here, right? And that's D3 and D4 on. And then current goes negative, where S3 and S4 are on. And then there's another negative section here. D1 and D2 are on. Okay? Yes, ma'am.
Is that time a bad thing or a good thing?
Dead time? No, dead time is not a nice thing to have. Because you lose duty cycle. You lose control. You don't have control. I mean, the current will flow. It's not, you're not controlling it yet. It's not up to you. You have to have it. I mean, can you, as soon as you turn off the switches, current will flow through the diodes. What if you didn't want that? What if you wanted to, if it flows through the diodes, you cannot interrupt it, for example. What if you want to interrupt it somehow?
Would you switch on to interrupt the diode?
You will turn on S3 and S4 afterwards, right? You will turn on S3 and S4. So we turned on, after the current started flowing in the diodes, we turned on S3 and S4. But I cannot turn on S3 and S4 soon, I mean, so fast. I mean, there has to be a finite amount of dead time that I keep. Actually, it's not very relevant when we talk about switching at 50 hertz. Because when we're switching at 50 hertz, you are switching your switches at 50 hertz, so it's not a big issue. Right? So I want to switch this switch every 50 hertz only, and these switches every 50 hertz only. I'm not worried about doing this faster than 50 hertz. But when we talk about having multiple pulses per switching period, then it becomes a problem. It's not a problem here. That time is here. It's not a problem really. It's not. We don't care to control anything here. We're doing this at 50 hertz. I want to switch only at 50 hertz. So I would like current to flow in the diodes for this period of time. But if I have many multiples of these switchings happening in a single period, the number of these switchings that I can have in a single switch, in a single full period of the fundamental waveform is going to be limited by the amount of dead time that I have. Right? If you have to maintain a huge amount of dead time, then it eats away from your switching period. Right? So if you're eating away from your switching period, then you're going to limit the amount of switching frequency that you can, raise the amount of switching frequency that you can have. So if you limit your switching frequency, then you have to live with two things, maybe larger inductors, larger capacitors, right? If you want to maintain the ripple within a certain value, right? Something else. Yeah, basically you will limit switching frequency and you will have to live with larger reactive components, yeah. Yeah.
Now that you mentioned when you have a larger inductor,
Yeah.
Just the current ripple will reduce, right? Or will something else change as well?
No, but here the inductor is actually your load, right? So here the inductor is actually your load, but in the case of multiple switchings per cycle, yes, it's the current ripple that will change, for sure. But in the case of multiple switchings per cycle, we want to create a sine wave. Here, is this a sine wave? The output, is the current a sine wave? It's not a sine wave. It's a highly distorted waveform that we really don't like, but it's an AC waveform. So if you have an AC motor that you plug across this voltage and this current waveform, it will run, no problem. But what we want to get to is something that looks like a sine wave, and it will have, we will be switching multiple times per period and creating something very close to a sine wave. Sure, in that case, if we want to maintain this ripple low, sure, that's the inductance is something that we can add to maintain lower ripple, yes, sure. I don't know if I answered your question. Yeah, in this case, I was just talking about the RL load. But if you want to control, here I'm not really controlling ripple because I'm not I'm switching once per period. Right, so this is my ripple is my output current here. It's my peak-to-peak output current. I don't really have the notion of ripple in this case. But here, my peak-to-peak output current, for example, is this. This is my peak-to-peak output current value, but I have ripple here that I would like to maintain with a certain window, within a certain window. How do I achieve that? I cannot achieve that with fundamental frequency switching. Here, what we're doing is fundamental frequency switching. I'm only switching at 50 Hertz. This is 20 milliseconds. I'm switching one time. This is S1, S2 on. And then this is S3, S4 on. The diodes, I don't have to turn them on. They're already there. So here, what happened here was current was flowing through S1 and S2. What happened here, current was flowing through the corresponding diodes, and diode D1 and D2, or D3 and D3 and D4, right? So here I had D3 and D4. Here I had S1 and S2. And here I had D1 and D2. And then here I had S3 and S4. Current was flowing through them. But I only switched S1 and S2 once at the beginning of this period, and then I turned them off here, right? So this is my switch signal to S1 and S2. My switch signal to S3 and S4, right? I only switched them once during this fundamental period, right? So I'm not really controlling ripple as such. The output current is the output current that looks like this. If you're going to talk about ripple, then this whole thing is ripple, right? So the notion of ripple does not exist here. Okay, so we move to we covered this. We now have a justification for putting this diode and MOSFET, or diode and IGBT, right? Everybody's happy with why we put now a diode and a switch, not just a diode or not just a switch. And here they drew whatever we were talking about. So S1 and S2, and then before that with the corresponding diodes, D1, D2, and then D3 and D4, etc., etc. So these were the various the devices that were conducting current at the various times. And then we said, our objective is to finally get a nice waveform, nice voltage waveform that has as much of a sine wave-like fashion as possible, as well as the current waveform, right? So because that's our objective, of course, I have to do some analysis to look at where I stand now, so I can work on improving it, right? So the analysis will be based on Fourier series. We will not analyze the current waveform. We will not derive the Fourier series for the current waveform. We will go to our Fourier series for the voltage waveform. So for the voltage waveform, we have a square wave. Its Fourier series is V max over pi sine omega t plus sine 3 omega t over 3 plus sine 5 omega t over 5, etc., etc., right? So this is easy. We can analyze that. We take the different components of the voltage Fourier series, divide them by my impedance at every frequency, and find the current at every harmonic frequency, right? And from there, I can work on calculating RMS value. I can calculate THD. I can calculate crest factor. I can calculate whatever I want to calculate from the chapter 2 calculations that we did, right? And so that's what we will have to work on. So again, the peak value of the voltage is 4 VDC over pi, and if it's n is the fundamental, which for 1, third harmonic, fifth harmonic, etc., etc. and then the current will be the voltage divided by the impedance at that specific frequency. And then again, we said we can calculate the RMS current, calculate the power, we can calculate the THD, etc., etc. So they did this for us. They calculated the voltage harmonic, the impedance harmonic, the current harmonic, and the power, right? I mean, is everybody okay with how do we do that? How we do that? So the equations for that are here. The voltage harmonics are from the Fourier series. The current harmonics are from this equation, and this Zn is basically the square root of r squared plus n omega L squared, right? All under the square root. And then the equation for power is it's because here they have the real power will only be dissipated in the resistive load, so you can use V times I cosine phi, but it's very difficult because you don't have you can calculate the angles of the impedance at every frequency, and then from this equation you can calculate the V n times I n cosine phi n. You can do that, or since I'm looking at real power, I know that real power is only going to be dissipated in the resistor, so you can use IRMS squared times R as well, right? So that's another way to do that, to do it. And then, of course, you don't calculate everything until infinity. You will calculate something until a certain harmonic. I will tell you, for example, do it until the 5th harmonic, do it until the 7th harmonic, or whatever, right? It's going to be close enough because at some point, again, the voltage harmonics become very low. The impedance at a higher frequency becomes high because n times omega L becomes a large value, right? So the current harmonic becomes negligible, right? So at some point, you're not adding much to your RMS value anyway. So how much is that? Depends on the shape of the waveform. So it can be up to the 5th harmonic, 7th harmonic, 9th harmonic, whatever. You will be told, for example, if you're asked to do that. Yeah. So here they do this for us, and they do the calculations for that square waveform up to the 9th harmonic. So there's the frequency, the voltage harmonics, the impedance at the various harmonics, the current, and obviously you see this is a lot smaller than the 9.27 fundamental, right? And then the power at the corresponding harmonic, right? So you see, but the amount of power dissipated fine at the 3rd and 5th is not a lot, but it exists, right? I mean, there's power at the 3rd and the 5th components that is, not very significant, but it is significant to some extent. Yeah. So we would like to see a lot more of that on the fundamental. We would like to see a lot of that on the fundamental side because we would like to see a nice, beautiful sine wave and a nice, beautiful on the current and the voltage. If we do that, then all the components will be producing real power, and they will all be, because eventually we would like to create a voltage waveform that looks like a sine. If my voltage waveform looks like a sine and my current waveform does not look like a sine, I have a lot of power dissipation that's not contributing to real power. Here I have, I have something that is contributing to power at the 3rd and 5th and 7th. It's a little bit smaller, and the 9th as well. Yeah. So what happens if I improve my waveform? If I make my waveform closer to a sine wave? We talked last time about this waveform, right? We said that if I add zeros here, I become a little closer to a sine wave, right? The other thing I should have said, okay, it's these 3rd harmonics, for example. Here I have a simple RL load, but for a motor, for example, if you provide a motor with something besides the fundamental, you will not just get real power. In a resistive load, you will get real power. But a motor does not operate in that fashion. A motor, if you don't supply it with a 3-phase balanced load, meaning only fundamental component, what happens is these 3rd harmonics and 5th harmonics, they will cause heating because they are actually torques, but in the opposite direction. So the way we would, there's a mathematical theory called symmetrical components. We will study extensively in 459, symmetrical components. And symmetrical components theory says the following. If I have a three-phase balanced system applied to a three-phase load, I will have three-phase balanced currents flowing the load, right? If I have something that is not balanced, if I take, this is larger than, this is, let's say, A, this is B, and then this is C. This is larger than B and C, right? This is not balanced, even though they're 120 degrees apart, for example, but they're not balanced. So in this case, I cannot do this single-phase equivalent circuit business that I was doing, right? Do we agree or not? The single-phase equivalent circuit works fine if the three-phase voltages are balanced, because then the three-phase currents will be balanced, and then if I have a load, the currents will sum up here to 0, and no current will flow of my neutral, so I can connect the neutral of my source with the neutral of my load and extract this outside and do a single-phase equivalent circuit, right? That's the whole story behind balanced systems, right? If the system is not balanced, if I'm supplying it with something like this, I cannot solve it. You cannot solve it using single-phase equivalent circuits. You can keep it as a you can keep this circuit like this and do a loop here, and a loop here. You can do that because this is a circuit. Kirchhoff voltage law will apply, and you can try to solve it this way. But you will have a big set of equations that will all be interdependent on each other. And then it's simple with one source and one load. But can you imagine in a power system? In large power systems with tens of generators, tens of loads, it's not that simple to do something like that. So in a large power system, we need to find a way to simplify our calculations so that we can always go back to a single-phase equivalent circuit or something that looks like it. And that's what symmetrical components theory does. Symmetrical components theory tells me that if I have a voltage source or a current source that is not balanced, I can chop it up. This is an unbalanced source. I can chop it up into two balanced three-phase sources, but one, okay, so if this is A, B, and C, right? One will look exactly the same. It will have the same sequence, right? If you're standing here, these are phases. They're rotating with time, right? They're actually changing with time. This is a frequency. They have frequency content there. If you're standing here, you will see A first, then B first, then C, right? And this is called the sequence of that voltage supply. So let's say we will call this positive sequence. So an observer will stand here, will see phase A, phase B, and phase C. Same thing, if you're measuring, you will see phase A first, then phase B, and phase C. That's positive sequence. So what symmetrical components theory tells me is that I can take this unbalanced system and I can chop it up into a positive sequence circuit, a positive sequence supply, meaning this is A, this is B, and this is C, rotating this way for an observer standing here. A, B, and C, right? And for an observer standing here, A, C, B. So for an observer standing here, I will now see something different. I will see phase A, then phase C, then phase B, right? It's like standing here and having this rotate the other direction, right? What would you see? You see A first, then C first, then B, right? So A first, then C, then B. So this will be negative sequence. What did Dr. Haytham say in the 338 course about flipping? Do you agree with, this is what the symmetrical components theory says, right? It says that I can take this, chop it into a source that looks like this, and then do what? Take this and apply it to my three-phase equivalent circuit. This is balanced, right? If I apply it to my three-phase equivalent circuit, what can I do? Solve it using a single-phase equivalent circuit. Nice and simple, right? Same thing, I can take this, apply it to the same circuit. Nice balanced three-phase, use single-phase equivalent circuit. And then it's another, you take this and chop it up to what's called positive sequence, negative sequence, and zero sequence. Zero sequence is, these will be the three-phase voltages, but they will all be in phase, right? I don't want to talk about that too much now, but actually we can, because when you are supplying a motor, applying positive sequence balance, what happens? You produce torque, right? But what happens if you flip the terminals, Dr. Haytham was saying in 338? For those who took 338, I mean, it's not a requirement. If you flip the terminals, what happens to the motor in that case? Induction motor. Who took 338? Okay, what happens to the terminal, to the motor? Come on. You don't remember? So the motor will change speed. I mean, will flip. The speed of rotation will flip. The direction of rotation will flip. It will be the opposite direction, right? So again, these three phases, what are they doing? They're creating a rotating field inside the machine. This rotating field, again, I'm not going to go through the theory of how to generate a rotating field, but this rotating field will rotate in a certain direction depending on the sequence of the supply. If you flip the sequence of the supply, the rotating field will rotate in the other direction and you will rotate in the other direction. Okay? But now it's like taking what? It's now you're taking these, when you have an unbalanced supply, you're taking the field in one direction. And you're putting, at the same time, it's superposition, right? This is, I said, this is equivalent to these three together. But this can be 10 volts, this can be 1 volt, this can be 1 volt, for example. If it's an unbalanced system, they don't have to be the same magnitude, but this can be 10, 1, 1, 1. These are the balanced three phase, but 1 volt, 1 volt, 1 volt. This is 10 volt, 10 volt, 10 volt, 1, 1, 1, right? This is positive sequence. So the motor will rotate in one direction, right? You're also applying, at the same time, a negative sequence, but with a lower value. So what are you trying to do? You're trying to rotate the machine in the opposite direction. If you apply voltage, you will have current, right? So you will have current in the winding, but what is it doing? You're actually decreasing the torque. This is actually opposing the torque produced by the positive sequence, right? So you're heating up the motor. So you're not going to get the same amount of torque. You brought the torque down, and what happened to the current? It went up, because you added some negative sequence current to your machine, right? So you had the positive sequence current contributing to torque. Then you put a supply in the opposite direction on the motor, trying to flip the direction, right? So what did that do? That supply, superposition, right? It's the source, and you have an RL load. I mean, same, superposition, current will flow, so you have to sum up the current. So that current will be additional current in the winding, and it's going to push torque, generate torque in the opposite direction of the positive sequence, meaning it will reduce torque on the output shaft. So you've reduced torque, and you have more current in the machine, right? So you're heating up the machine, basically. And then Dr. Haytham maybe talked about braking. No, he did. I'm sure he did. I'm sure he did. I'm sure he did. What did he say about methods of braking induction motors? No, he did. I'm sure he did. Huh? DC braking. DC braking, plugging or DC braking, right? So this is like DC braking. You're putting, DC is what? DC is a DC is a voltage in a, 1 voltage in space, right? One value of voltage in space. Is it rotating? No, it's not rotating. So same thing. This is not, it's a voltage that all three voltages are in phase. So if I have three voltages that are in phase with each other, I apply them to a three-phase system. They're not balanced. I mean, they're not a balanced three-phase 120 degrees apart anymore. So if they're all in phase, what happens? The currents that they will generate will also be in phase, right? So if you apply them to a three-phase system, right? These are three-phase voltages. They will apply them to these three resistors. These are all in phase. They're not 120 degrees apart. So what will be the sum? 0? It will not be 0. It will be something, because these are all three in phase. These are three voltages that are in phase. They will cause current. So it will not be a balanced system either, right? These will be like plugging the motor, like applying a field in the motor that is stationary, right? Only three-phase balanced systems, balanced phasors that are applied to a three-phase load will generate a three-phase rotating MMF. If you can do that, you can generate a rotating MMF with also two phases 90 degrees apart. That's single-phase machines operate in that fashion. If you put a voltage on one phase and a voltage 90 degrees apart, or if you've played with motors in a fridge, right, you would typically have a capacitor there, called a capacitor, a starting capacitor. Single phase, you talked about single phase motors in the class, right? 338, you talked about single phase motors, right? And you remember Dr. Haytham putting a capacitor in there to the starting capacitor, right? What was that capacitor doing? Why was it starting? Yeah, it was creating this phase shift because you only had a single supply, right? You had a single supply, but this capacitor is phase shifting by 90 degrees, taking the voltage, phase shifting by 90 degrees, and applying it to a second phase. When you do that, you have two phase voltages that are 90 degrees apart. When they rotate, they generate a rotating MMF. But now I have this. These are three in-phase voltage supplies that are not going to create a rotating MMF, but they're going to create current in the motor. This current will create torque. That torque is not going to rotate. It's stationary torque. Right? So this can plug the motor, can break the motor. This can rotate in the opposite direction. And this will rotate in the direction you want it to rotate. So if you have too much of the negative sequence or too much of the zero sequence, it's a problem. Okay? Why are we talking about all this? Yeah, because the third harmonic, again, that's in 459. We'll talk more about that. But in the third harmonic is a negative sequence, as seen by a motor, right? When it will be a third, it's a negative. Sorry, the third harmonic is a zero sequence. Fifth harmonic is a negative sequence. So if you have a negative sequence, power in the negative sequence, power in the zero sequence, then what are you doing? You're going to be breaking your motor, heating your motor, not contributing to torque production. That's why I was trying to explain that, right? So in an RL load, it's not very clear. Okay, fine, I'm generating real power. What's your problem, right? But if I'm applying this to a machine, then it's a problem. So that's why I would like to improve it. And the biggest chunk of industrial loads are motors, right? So you can, that's the justification. Justification is, okay, you cannot live with low-order harmonics that are producing power, because then you're going to be heating up motors unnecessarily without producing the torque that you require. So you're going to have to derate all your equipment, which doesn't make sense. You derate transformers, derate motors, etc., etc. So how do you solve that? You try to improve the harmonic content of your waveform. How do you improve the harmonic content of your waveform? You cannot do it with a pure 50% duty cycle fundamental frequency switching.